There is some blinking going on.
15 seconds or something.
Okay, so very often when you have a vertical crack, magma crack, it's called a dike, and when it's horizontal it's called a seal, although actually seal, the proper name would be when it goes between bedding, you know, different layers of rock. But very often people call it seal anyway, whatever. If it's horizontal it's called seal, and if it's vertical it's called dike. And in general, the preferred orientation is not like always the very strict rule. It's more like a tendency, a strong tendency, is that they are oriented according to the principal stress in the way shown there. So basically you have always, probably you had a little bit of elasticity, right, where you have a strain tensor, or a stress, you diagonalize it and you figure out the principal stresses. Often they are supposed to be vertical, but this is not necessarily true. It's definitely vertical at the surface, because you always have that the free surface is stress-free, and therefore one of the axes is always vertical. But as soon as you go a bit deeper, you can have different effects, and this is not true. Anyway, you do this, diagonalize, and you end up having three stresses. One is most compressive, one is least compressive, and then one is intermediate. They are often called sigma 1, the most compressive, and sigma 3, the least compressive. It depends on the assumptions, if they are positive or negative. Like you.
Geophysics are compressive is negative, is that positive?
Yeah, it's conventional, and actually geophysics is very different. It
Mm-hmm.
depends if people are more geologists or more engineers,
Yeah.
or more physicists, what they use. Like more engineers, they use extensional positive and compressive negative, and geologists use the other way around. Yeah. Yeah, so you always have to pay attention. And actually, there are even people that invert the names sigma 1, sigma 3. Like I've seen everything. So you need always to specify. Even when you write your paper, you always specify the most compressive stress axis, comma, sigma 1, because otherwise people will get confused. Okay, so it is observed also in borehole. This figure down there is like a schematic figure of a borehole, that when the boreholes break because of pressure, this crack is oriented according to the most compressive axis. The reason is that you tend to open a crack against the least compressive axis, because when you want to open, it's easier for the medium to open towards a direction where you don't have so much compression. This is relatively intuitive, so it is clear. This will also answer partly to the question that you had before. It is clear that this orientation is not the same as the orientation of faults, because faults are they have a friction, and so they are generally oriented according to 30 degrees, something like this, of the between sigma 1 and sigma 3. This is the orientation of fault. However, if you have weaknesses that are not faults, so faults are optimized for shearing, while not all weaknesses may be optimized for shearing, you know. So the reason why dikes don't take faults is because generally faults are oriented in a different way. They are oriented in a way that for dikes is not optimal, because those are shearing planes, they are not opening planes. So it wouldn't help a lot to accommodate magma if you have actually total shearing on those surfaces, right? It's actually not convenient. However, if you have joints, which is a name used for actually opening fractures that then are closed, you know, it's like a crack that is oriented according to an opening criterion, then they may be used. of course, then if there is a pre-existing joint that allows for opening, then this is going to be used. But these cracks have their own pressure, and they can also open their own fractures as they prefer. Okay, so let's go ahead. Like, look at this case. This is a very, very beautiful paper by Roman and Jepard, where you have, first you need to look at the purple dike. The purple dikes are, like you see, the dating is 26 million years. They are the oldest, and they are all parallel, more or less parallel. And this was the direction of the sigma 3 at the time, perpendicular to the sigma 3 at the time, and aligned with the sigma 1 at the time, like a tectonic stress. They are all parallel. But then what happened? A volcano was born over maybe a couple of million years, and then you have all the dikes that are younger than the date of the magma chamber. You see, the magma chamber is like 24.6, 23.9 millions of years. They are all actually oriented in this spider shape that we also saw on the planets, you know. And so this paper does a lot of calculations to show that actually the main control is not because previously this was explained as a magma chamber effect. Like, you have the magma chamber, you pressurize the magma chamber, and this is what causes the dikes to go. Basically, you reorient sigma 1 all radially to the magma chamber, and sigma 3 circumferentially, and this is what causes the dike to be all radial. However, this paper calculates the effect of this and also the effect of the big edifice that you would have. And they see that if you use a magma chamber stress plus tectonic, the curvature of the dike should be much more curved like this. So like with a much sharper curvature and much closer to the magma chamber, while the curvature is not very sharp. And then they explain this only with the load of the big edifice. So you have a big edifice that is pushing and also reorients all the stresses. Sigma 1, the push, will put sigma 1 also radial, but in a way that is more gentle, because you have the gentle slope of the volcano. This is the figure. So basically they put like a conical load of radius r and height h, and then they show that depending on the strength, so these two are two different patterns for a different amount of loads. If you vary h with respect to the tectonic stress, if you vary the amount of load, then you get that tectonic stress may still win, or the load may win, you know. But anyway, if you go far away, so this is, I think the circle is exactly this R, like when the base of the volcano, you see that after the dikes escape from the base of the volcano, they tend to curve and they go according to tectonic stress. So this is actually really what happened in the Bardalunga case. It went sharp. Here is all smooth, but so this is there are a few numerical approaches to get the trajectories of dikes, and they have all been developed. The first ones, actually here one is missing by another scientist, I need to remember to add it. Around the year 2000 it became kind of popular. There were a lot of papers on the propagation of these cracks and what direction it would take. And then it was just a few papers and people abandoned the topic. It was just a few papers, and then these people didn't do it anymore. until more papers came a bit later. So basically, how do this method work? They are all boundary element approaches. Boundary element is like a numerical method. Do you know more or less what it is? Also finite element. Do you know the difference between these two? Okay, these are all methods to solve the equations of elasticity in a medium. Finite element means that you mesh the entire medium, and you, at the nodes of the mesh, everywhere, you say the equation of elasticity needs to be satisfied here. So basically then you say everything which acts in the medium will have an effect on this point, and I will write the big equation, and this needs to be equal to my boundary conditions. For example, at the edge, you need to satisfy the boundary condition in the elements at the edge, and you need to satisfy everything in every point of the medium. So basically what you end up having is a big matrix with a lot of equations in number equal to the number of nodes. Okay, and your boundary conditions will be also given and everything. And then the methods are, the challenge is to invert these big matrices and to do it in an efficient way that doesn't take ages. So generally these methods are, so there are a few codes that are finite element that are have been coded by scientists, but actually it's also a very commercial method. There are COMSOL is a famous finite element code, and then there is Pilot that is used for tectonic calculations, elasticity in like in subduction zones, or you have COMSOL that is used at every scale. It's a commercial one. And then boundary element is like one step towards analytical. Basically, they solve the elasticity equations due to a point source. For example, you have one individual dislocation, just one dislocation. For example, in this figure, it would be one of those segments. And you have an analytical solution that tells you, if I open this dislocation, this individual dislocation by a given amount, then I have a given stress field and displacement field everywhere in the medium. You can have a free surface already included in the analytical solutions, for example. And generally they are unbounded, so you have an infinite medium. You can have a free surface. There are analytical solutions for 2D dislocations that they are in plane strain, so it's infinite in the other direction. You can have 3D solutions with rectangular dislocations, and there are also solutions with triangular dislocations. And you can have them opening, or you can have them shearing, and you know analytically the stress and displacement field in the entire medium. Okay, then what do? You compose a few of them, like in the figure you have some of them, and then you say that only at the midpoint of each dislocation your boundary conditions need to be satisfied. Like in this point in particular, what you say is that in the middle points, those red dots, black dots, you say, I want to have 0 shear stress, and I want to have a given pressure that I want. For example, 5 megapascal, which is the magma pressure. 0 shear stress because it's a fluid, so I want 0 shear stress because shear stress cannot exist, it's a fluid. And I want magma pressure 5 megapascal in each of these dots. Then you have a number of equations that is only not the entire medium and all the nodes, but just the boundaries of my field, everything that is not analytical. So in this case, just the dike, you know, just the dike you discretize. You discretize in different elements, and then you have this number of equations where you say, for example, in the number 1 point, I solve one equation, and this equation is the effect of dislocation number 1 on this point, you know, so you have a green function, like for example, number 1 and number 1, so actually its own dislocation will have a given stress in this point, times the amount of opening in the dislocation number 1. Then you have the green function in the location number 1 by dislocation 2 times the opening of dislocation 2. So basically, every dislocation will have a stress on the first dot. So you sum up all the contributions of each dislocation, the same one and all others. Each one will be proportional to the opening of that dislocation because everything is linear. And then in the end, so you have all the dislocations, and then in the end you say, I want here 5 megapascal. It's my known boundary conditions vector. So basically, if you do this for all these locations, you end up having like a matrix of green functions times a vector of all the openings of all the dislocations equal to all my boundary conditions. So you invert this linear system, and then what you get is the openings of each dislocation, exactly each dislocation. How much do they need to be open to reproduce exactly the magma pressure that I want, and also to have the free surface and to have zero displacement at infinity, and you know, everything is already satisfied because each individual analytical solutions already satisfy zero displacement at infinity, and they satisfy the free surface, and all together will sum up exactly to reproduce exactly my boundary conditions, which is zero shear stress and my pressure, magma pressure on the dark plane. Okay, this will give me the shapes. Solving this linear system will give me this shape. It will be thinner and thicker, depends how much pressure I put, right? I can put a gradient. I can put a gradient because, for example, my dike is filled with buoyant magma, and therefore the pressure inside is not just one constant number, but it is varying because I have delta rho times G as a gradient, and so therefore I have more pressure at the top than at the bottom, because it's at the bottom I will have more lithostatic stress than at the top. So basically I create a gradient in this way, and I get my shape. Okay, this is the first step. The second step is to say, okay, I want to extend this dike. I have an excess, the magma chamber is pumping in volume, for example, or simply I want to check whether this crack out of its own energy will extend. Okay, then what do? You add at the tip another dislocation, and you add it according to several angles. And then you virtually elongate the crack. So you do the calculation as if the crack was extending into that direction, and you do it in many directions. And then you check how much energy you basically have in the new configuration. Did you release energy of the elastic energy, or do you need to put energy into the system to actually do this? So if the magma is buoyant, you will find that actually generally you release energy if you propagate the crack at towards the Earth's surface. Therefore, this propagation can occur, and you need also to compare the energy that you release during the extension with the energy required to actually break new surface and create new crack surface. This is called the fracture toughness. It's a parameter. What happened? It's because I didn't use it?
Yeah.
Okay. It's called fracture toughness, and it is a parameter that you can measure. And basically then you can compare the energy that you use with the energy to create this new piece of crack. And if your energy that you release is larger, then yes, my propagation will occur. And then what do? You really extend the crack in the direction that you want, and then you have to recalculate the entire shape. It may happen, for example, that you want to have a constant mass propagation because you the magma chamber is not pumping any more magma. You want to see whether the crack can propagate by itself without adding new mass. Then you recalculate the new shape. It may happen that the last crack at the bottom compenetrates. You get a negative opening. Then you know, okay, I need to close this dislocation. Then you recalculate everything, you know. So in this way you are able to calculate what direction the dike will take. This particular figure comes from either this paper or this paper. One of these two, I can't remember. And basically it is like a new like the method that was already presented around the year 2000 was used again. And this is an example of how you can use this. So you first calculate a stress field, maybe using also some analytical solutions for loading at the surface. So here you put like a volcano, and then you calculate the entire stress. This is very, very similar to the other paper, Roman and Jopard. They calculated the stress due to the cone. Just they did it in map view using axisymmetrical loading sources. Here is in plane strain, so actually everything is you have only this cross section, everything is equal. Otherwise, if you go in this other direction here, so basically it's not really a volcano, it's more like a ridge. But I mean, the results are not going to be incredibly different. They just will become more axisymmetric. So in this case here, the dikes are born from a location here, for example. They are not interacting with each other, these dikes. It's just to show that if they start in a direction that is not vertical, they will actually bend. And you see, not in every point they are according, the sigma 1 is these segments. And you see they are actually like this. Sigma 1 is always more or less towards the volcano. So you can see here many things. The first thing is that if you calculate this kind of stress, all dikes more or less will be attracted to the volcano, because you see already from the sigma 1 pattern that this is what is going to happen. But you also see that if you really check step by step, and for some reason, for example, there is a magma chamber there that will actually lead the dike to actually start in a different direction. The dike will take some time to align to the sigma 1. It's not like an instantaneous readjustment. The dike will take some time, but eventually after a few, like a dike length, something like that, it will be more or less aligned, and then it will go up to the top. Here you see in the one to the left that the dikes stop before reaching the edifice, while in the other one the dikes reach the edifice, reach the surface. If you see, basically what was done is the second ones were bigger, they had twice the mass. So basically if you have more mass, then and they are buoyant, then you have more buoyancy force. And you can overcome this pressure, intense pressure of the edifice that will tend to actually squeeze the dikes and attract them, but squeeze them at the tips and keep them down. So you can see here why also you form a magma chamber, because you form an edifice, and then the edifice at some point will tend to attract everything, but keep it there. And then if you have supply of heat, if you have supply of magma, then you can create also a wider volume of melt, because you will erode some of the country rock, and you will have more magma coming in and create like something that is like more of a magma chamber. And then this will actually go deeper. There are a couple of studies that are in preparation. I've seen one from Claude Jopard, and there is also a student of mine who was here a couple of years ago, like one of you. She is doing the calculation of when you grow the edifice, the magma chamber is actually supposed to actually go down. So the bigger the edifice in general, you also have other contributions because you may have different tectonic stress and so on, but all equal, all being equal, if the edifice is bigger, the magma chamber will be bigger. Yeah. And if you cut the edifice and if you decapitate the edifice by a big collapse, something like this, then instantaneously you can have it shallower. So, and magma will tend. And actually this is seen because you remember that I told you that magma composition depends on the pressure, because at the different pressures you will have a different chemical equilibrium. So actually you can check this, and in this paper by Claudio part, he did exactly that. He checked compositional variations related to a different load due to a different history of the edifice. It can be a big collapse, but it can be also the melting of an ice cap, like we had glaciations.
Yeah.
And when you melt the ice cap, then the depth of the chambers all change. Yeah, so next one is actually what happens if you start from the side, and again you can see that depending on how they start, they will go one way and they will go to the edifice, or they actually can go even the other way and then stop, because nothing more can leads them to propagate, because they become horizontal. If you have a dike, even if the magma is buoyant and it becomes horizontal, the buoyancy force is gone, because you don't have a bigger variation. Yes, you can integrating over that, you don't reach any big value, right? Exactly. And so then this is how it looks like. And then more stuff. This is the first example of a gelatin experiment that I'm showing to you. It's by this person, Watanabe, Japanese colleague, and the block here is gelatin. Oops, here is gelatin, and then here you have an injection of fluid into the gelatin, and you create this crack. This is seen. So if you saw the crack from the other perspective, it would be like a dike, you know, like round like this. But if you see it like this, then you see the cross section. And if you put some bricks at the top of the gelatin, then you create this loading effect, and you can see that it really goes there. The dike goes there, and then it stops just before before the mass. Okay, this was another paper, McAfee et al., where he looked at the effect of having a layer. So basically the dikes start all like this, and then here you have a layering, you have a more rigid medium and a less rigid medium with different elastic ratios between the two media. And then you can see that you have, basically you have something like, looks like optical refraction, you know, where you have like a direction, and then they go more vertical if you have less rigid medium at the top. And here is the energy of propagation, and one can see that the energy stays the same more or less during propagation, because what you gain, you lose more or less if you are in a homogeneous medium. But then when they go very close to the interface, they actually tend to accelerate, because you have a lot of energy release, and the reason is that you have a less rigid medium at the top, so the dikes will tend to open a bit more, and then this makes a big release of energy. But then as soon as the dikes penetrate into the new medium, they will slow down, but then you see that the energy goes a bit higher than here, because the release of energy, they will be thicker, shorter and thicker, and then this is the new energy level that they will have. So they will go probably a bit faster. This is the same, but with actually at the top there is a more rigid layer, and so if you do this, you will see the opposite effect, where you have the tilt will be actually more, and also like similar to optics, there will be a maximum. Like for example, here is not really, he didn't really calculate the maximum, but already when you have 0.2 ratio, they will go flat. And this is one way in which you can produce a flat dike. One way we saw it before, like with just stress. The volcano is there, the dike doesn't go really according to stress initially, and it tends to go flat, and then there is no way you are going to move in this dike anymore. And here is another way. You have a tilted dike, and then a more rigid medium at the top, the dike will just go flat, like this. And then actually stop. You see that the energy goes down, is the opposite as before. The energy goes down, and therefore it's also a way to actually stop dikes, because if it goes down enough that the energy released is not enough to break new surface, then you're going to stop the dikes. Okay, this is another geological problem that you can solve with this approach. This is a figure, I think this is also from Afar, I can't remember, or from Iceland, one of the two. And this is a graben structure where you have some fault scarps. Like here is like a fault scarp. So here is lower than here, and here is even a bit higher. And the volcanoes are actually on the highest point of the fault scarp. So basically, if you, I don't know if there is another figure, yeah, here. This you see really often. I've seen it also in the field. You go in the field.
It's not
This is not. It's, yeah, this, you look at the trees. Because in Iceland it's exactly the same, you don't have the trees.
Yeah.
And
there's no ice here.
Yeah, okay, but not everywhere in Iceland you have ice. In winter, but in summer you can have also no ice. But then it will be less red. The soil is red. Yes, but the figure, I have a photo somewhere of exactly the same thing. You go to the field, you see a fault scarp, and then you see a volcano on top of the fault scarp. So, if the magma was attracted by the fault, you would see the magma leaking below the scarp, like here where the fault is. And anyway, why is the volcano, you have a fault scarp like this, like a big step. Why is the volcano here and not here? You know, why is it on the highest point? Why did the magma choose to go all the way up to there if it could have had an eruption in the lowest point? So definitely this is there must be a reason, right, that it is more convenient for the magma to do so. So this is just the proportion of cones that are on the footwall, so basically on the highest point, and very few are on the hanging wall in the lowest point, because these are all normal faults. So this, basically the application is this, that if they are actually originating everywhere below this big graben structure with a lot of steps, many of them will tend to actually go to the highest point, because even a fault scarp, just 60 meters or 40 meters, the difference in load will be enough to attract more dikes to this more loaded position, and then have the eruption at the top. Of course, this effect cannot be very deep, but it can still be significant if the dikes start somewhere. So so this is just a small application at this small scale. This is another application in actually here is a bit I don't know why it came all together. I didn't pay attention to separate the things. Anyway, I'll try to explain. Okay, now have a look at this island. This is Fernandina in the Galapagos. Have a look at the distribution of the fissures. So the fissures are radial. We have seen that radial fissures are normal at volcanoes. And the reason for the radial fissures is that the topography and the load controls the dikes to go radial. But here there is also a rim of the calderas in the presence of a caldera at the top. And around the rim you have actually the fissures are circumferential, they are not radial. And it's actually a special pattern, you don't see it very, very often. So the point is, why do you have this? Why do you have this particular distribution? So previous models were like using caldera faults, like you have the faults. So maybe they go to the rim exactly because you have some fault in there. Or caldera wall unbuttressing. It means that when you remove the medium, it's not supported here to the right, it's not supported here to the left, and it tends to extend, to stretch. And then basically you will have a sigma 3 that is perpendicular to the wall. And this definitely is part of the truth. And then again, a lot of people started to look at the perturbation of a magma chamber. Like here in this figure, you see what perturbation you would have if you have like a spherical magma chamber. And the stress caused by a spherical magma chamber with this topography. However, you would have radial dikes, because also magma chamber creates a similar effect than the edifice, although actually with a different scale. So this would be radial. If you have a flatter magma chamber, then maybe actually you would have circumferential, but they would go this way. They would go with the concavity like this. But then there was a paper with the crustal deformation. Again, here it's not separated. There was a paper with the crustal deformation by Bagnardi et al. In 2013 that showed what happened at this island, Fernandina, during some dike intrusions. And basically what he saw is that some of the dikes, first of all, the reservoir is always like a flat pancake, and you see that because like a more spherical source doesn't fit the data within the caldera. You need something more flat. You recognize, we will see it, you recognize also if it's more flat or more rounded from the distance between the fringes. So you look at the pattern of the caldera. Now here it's not really shown, but we will see that. You look at the pattern of the fringes within the caldera. If they are all the same distance between each other, if the distance does not increase in the fringes, like this fringe, this fringe, this fringe, this fringe, they are all thick the same, then it means that actually most of the deformation is like vertically directed. While if the fringes increase their distance from the center to the side, like this, they become bigger, then it means that the deformation is more like this. It's relatively intuitive. So basically it is seen that here all the chambers are like flat. You don't know below, you know the top that needs to be flat. And then in some cases, like here is covered unfortunately, but you can see that the dike went here. It started with this square dislocation, like this square dislocation is the model. Then it went slightly more oblique, and then it erupted as a circumferential fissure on the rim. While in this case here, it started like a flat thing, and then it did something like this, even. It started like this, and then it's tilted. And when it's tilted, it tilted, and then at some point, before becoming vertical, like this, intersected the Earth's surface, the volcano surface, and it made a radial fissure. So actually these radial fissures are probably not even entirely vertical dikes. They are just something in between, like a tilted dike that created a radial fissure, but started, so like in the plot there, you can see here, it starts horizontal, and then it starts to tilt a bit, and tilt a bit more until you have an eruption. Yeah, so this pattern, like that they go this way and then they go this way, is not consistent with the previous, with this magma chamber pattern. Because this pattern says, okay, if I have it flat, it may give a circumferential fissure, but they will go this way. Instead, they go this way. So it's a different pattern. So, okay, so we did this work with a postdoc of mine. He's called Fabio Corbi, an Italian guy, and we thought, okay, if you generally have a big edifice creating a load, what happens if you actually remove some mass from the edifice and create a caldera? It's actually the opposite. Instead of putting forces that push down to simulate the load of the volcano, you have to actually take some of these forces and pull, because you actually remove some mass, you create some unloading. On the other hand, one may ask, well, I'll show you that this works, and then we can discuss this approach. So basically what he did is he constructed, this is a finite element model, you see? This is the mesh, and in every node you solve the equations, and this was done with a commercial software called COMSOL. A lot of people use this software. It's very flexible, of course, because you can put everything in there. You can put the surface of the volcano as you want, and you can do many things. It's quite flexible. So he created like an axisymmetric volcano by averaging the topography of the island, Fernandina, and then he put some mechanical parameters, and then he calculated the stress in two ways. One is he created the volcano with its topography axisymmetric, and then he turned on gravity. So basically, suddenly, you have the body force of the volcano acting. So basically what happens is the volcano is actually 1 kilometer, I think, from the sea floor, but then from the sea level, but then it's actually 3 more below, I think, 3 or 4 more below. It's actually a big island. Then if you do this, you turn on gravity, what happens? You relax the body in this way, it compresses a bit vertically, it extends a bit horizontally, and you create a lot of stress actually by doing this. I imagine this, since I work also with this gelatin experiment, I imagine this if you actually put the gelatin in a bowl, and then you release the gelatin from the bowl and you put it upside down, the gelatin will, deform under its own weight, basically. So he created this assumption, and then he used a different assumption, which is the opposite. Probably the truth is in the middle. This is one end member. However, this end member here is probably not what actually really happens at a volcano, because a volcano is not created overnight as a big island. You have a first layer of eruption, and then many layers superposing to each other, and then this builds some stress that is actually difficult to model by itself. But then what happens? You have a lot of processes. You have earthquakes releasing some of the shear stresses, and you have intrusions. Every time you have a magma intrusion in the volcano, you basically orient the intrusion according to sigma 1 and sigma 2, and opening against sigma 3. And then magma will stay there and freeze. If you go after the intrusion and you measure your principal stresses, you will find that actually sigma 3 has increased towards sigma 1, because you have compensated the difference between sigma 3 and sigma 1 by putting some magma in it. And so you have increased sigma 3 towards sigma 1. Then you have another dike, another dike, another dike, another dike. They will actually, like in the island where we saw that they went flower, they will go in all directions because they want to compensate this shearing or inhomogeneity in the principal stresses. They will compensate everywhere. When it's already compensated, it's actually all similar. They will not go. They will go to another area where actually you see a bigger gradient. And then in this way, slowly, the magma will homogenize stress in the edifice and make all the principal stresses, they will tend to go equal. However, it's kind of a competition because on the other hand, you will erupt material and you will load again the island, and then you will have new dikes, and then you will load again the island. So it's actually not as straightforward to know what is the state of stress of a volcano. It is a complicated thing. And there are not many studies, so it's hard to say. But I think it is something in between, So but he did the two end members. One completely homogeneous state of stress, one gravitationally loaded state of stress. And now I'll show you the result of, actually this is already okay, sorry, because actually the gravitationally loaded is not here because it didn't work so well. So if you take the gravitationally loaded stress, basically what you obtain, that all dikes would go radial. This is absolutely the stress that would cause a radial dike, and this is intuitive because if you take a big gelatin mountain and you put it upside down once you have formed it, it will extend in this way, so you have all sigma 3 circumferential and sigma 1 will be strongly pushing for having vertical dikes. And this is exactly what you would get. So if you create a volcano overnight and you inject it, you will create a radial dike. However, if you have a completely homogeneous stress, and on top of this you put a caldera, because the caldera collapse was 1963, so it's relatively recent, and it created 300 meters of collapse on the island, the caldera. So basically it's like you remove this mass and you take it away. So basically these are the arrows there to simulate the creation of the caldera, the excavation of the caldera. Then what happens? Look at the stresses. If you do this assumption, then this is sigma 1, okay? So basically sigma 1, instead of being actually vertical, it becomes horizontal below the caldera because you have decompressed. You have removed the mass and decompressed. And so below the caldera you have all flat sigma 1. This actually may be the reason exactly why you have this storage that is actually a flat crack. Because every time you have a dike from below that comes somehow vertically, it will tend to turn horizontal, and this will be the most favored direction for the magma storage in the island. Because due to this excavation, you tend to have this horizontal flat storage. It's oriented according to stress. And then what happens if you release a dike from the storage? It will go towards the rim and then encounter, so the stresses are rotated because of this. Otherwise there would be, actually all of them would be vertical. But the presence of the caldera and also a little bit the topography and a little bit the effect that this is concentrated only here actually makes, so where you see a circle, it means actually that sigma 3 is radial. So here you have the combined effect of a mountain with the caldera in the middle. So you see actually that there is somewhere here a region where the dikes tend to first go this way, and then actually they are forced to twist because the stress on the volcano will tell them to twist.
I think they are always looking for high stress.
They
high stress because of the collapse. There is decompression at the top, just so here relatively at the flank
It will be more stress.
Yeah, so
I don't think they tend to go to the high stress. They actually have to go only when the pressure in the magma chamber is big enough. Because actually the high stress at the rim will actually tend to close the tips of the seal. So the seal will fatten and not propagate until it becomes relatively fat. And then it will be too full. And then it will be too full to keep it there. And then the dive will start. But then as soon as it overcomes the rim, then actually the rim is the point where you have the highest stress. Once it overcomes the rim, then it can go easily down. So the rim is actually having, it's like a barrier effect. It will keep all the material there until it's enough, until it's big enough. And then it will go and then propagate. And then when you have an eruption, since the eruption will be generally lower point, I mean, it's like a difficulty balance of stress. I always thought it would be good to have a calculation where you actually see that you have this barrier, and then when it goes down, and if you open somewhere on the flank, even if the magma chamber is deeper, it can be that you have like a siphon effect, where you know what a siphon effect is? Siphon? It's like, I remember when I was a kid and in the home of my grandparents there was no bathroom, there was no shower. And so my father built like a shower outside, and it was like a big wine with a tube. And then you suck into the tube.
The prayer.
And you will drain the tube, even if it needs to go up. Yeah. So
use it even for petroleum from
the ship
to maybe to the car or somewhere.
Yes, exactly. So I think it's similar, So you have a barrier, which is this rim, but then if you overcome the barrier and the dikes goes down and then you cut and you drain it, you can drain the magma chamber, even if you have a suction. Actually, if you think of it, when you have a caldera collapse, elasticity will actually tend to, well, you have a lot of weight on top of you. So this will help, but it will create a suction at some point, and still the magma will drain. And until you even collapse everything, and everything will be drained. It's like a sort of siphon effect, maybe not entirely, I think.
So why there is collapse, where it's going, the material at the top of the caldera?
Where is it going?
Yeah.
So we will have an entire day on this, but I can show you here. Do I need to repush the recorder, or can it doesn't matter? If I change it to Blackboard, do I need to?
You just change them.
Okay. So you can imagine it like this. Caldera. Maybe you have several levels, I don't know. Or maybe you have a big body, it's hard to know. Here you have folds. So if you drain this, then you don't support the roof, and the roof will just lie down. Like this. And we will have an entire day on caldera, so I will show you also with analog experiments how this works. Okay. Do you have any other question on the? Actually, if you overlap the inversions of crustal deformation data with by this Bagnardi guy with the model, it matches quite well, because you can see that it starts to bend and go up, or it decides to twist, and more or less it fits. So I think so it fits maybe not entirely because here the bending, the twisting occurs sooner in nature than in the model. You see, the model would predict that it occurs a bit later. Maybe this is a sign that actually the truth is in between a completely homogeneous state of stress and a fully gravitationally loaded state of stress. So like if I would do it again from scratch, the paper, I would now seek to have a different proportion, you know, to put like a bottom that I can tune, and to see what is the ideal combination of the two to match the observations. Here Fabio did also some gelatin experiment with a shaped volcano. Like he shaped it with a caldera and with a slope for the flank in a container. And what he got is that indeed that actually he got a vertical dike turning towards the caldera a bit not very, I mean, quite you know, close to the caldera. But so it depended on the overpressure of the dike, yes. So let me see. If the dike was big and very much overpressure, so like with a big amount of air, so these were air dikes, then it was not so much sensitive to the stress generated by creating the caldera. It just turned at the very last moment. You see, it's almost vertical, and then at the very last moment it turns a bit. Because actually it is a competition. I didn't see it very much in the model of the volcano with the dikes, but it is a competition between the buoyancy and the stress outside. So if the dike is very, very buoyant, it has a lot of buoyancy force, then the stresses outside will be there, but will have a smaller effect than if the dike is not very buoyant. So if the dike is barely buoyant enough to actually propagate, it will be very, very sensitive to the stress, external stress, and do exactly as stresses tell the dike to do. If the dike is full and big and full of buoyancy, it will just go its way. And then you have also there some intermediate cases depending on intermediate buoyancies. So you can see here in the result of this experiment, this dike is bigger and this dike is smaller, and it will turn much earlier. This one is actually erupting in the caldera floor, and this one actually it's erupting outside as a circumferential dike. Anyway, one result of this study was actually that one needs to be careful to do gelatin experiments with the I will tell you about this because we will have also a day on analog experiments. I will tell you why one needs actually to be careful. Anyway, one result was that depending on the buoyancy force and the loading, you need to, so you have a ratio. The ratio between the two will tell you the curvature of the dike. So the dike will curve very much if its own buoyancy will be smaller than the loading. Otherwise it will go straight. Okay, so actually another result was that maybe storage at caldera, so because we started to think that actually most instar pattern of deformation at caldera show that below the caldera you have a very flat storage system. And we started to think that actually this may be even an effect. It was thought before that calderas are there with this big hole because you have from the start a very big magmatic system, and therefore you have bigger eruptions, and therefore you create these collapses because the eruptions will be so big. However, the study proposes that actually there may be also, so it's not that this is going to be rejected, but there be also a control on the other way around. Like if you have a given load or a given pattern where you create an excavation, then it will have an effect on the shape of the plumbing system. And if you manage to create a caldera because you have a big eruption, then the next time you will feed a system, it will be more flat. And maybe it will also be there because the rim are pushing, and therefore you need to accumulate more magma to be able to overcome this push of the rims and to create an eruption. And then once you do it, you will drain it again, and then you create a new collapse. And basically you can create a caldera so you will increase the size of the plumbing system by creating the caldera, and so it may be an effect that helps the magma chamber to actually become bigger and bigger in these systems. Maybe it's just an hypothesis. Anyway, the fact that you have below calderas a layered system with a lot of these seals is confirmed by several experiments. Here was the figure with the... here if you put tectonic stress, but actually for Fernandina it's not necessary. Here is if you put extension and if you put compression. But this is not necessary for Fernandina because Fernandina is intraplate, entirely intraplate and relatively decoupled from any stress. This was the figure if you have loaded edifice, gravitationally loaded, so you actually have vertical dikes all the time, and they will go radial around. So this area here, they stay kind of they stay vertical, and then they go this way and they create a radial, like in the figure of the summer cone volcano where you had the magma chamber with some extent and then all the radial dikes. Okay, now I want to talk to you about rifting in general, which is similar. It's just like a similar thing. Okay, but if for a volcano it works that you create an excavation and then you command the dikes to do, specific trajectories. Maybe this works also at a larger scale. For example, when you create a rift. So, for example, in rifts, this is a figure of what you would expect, because you stretch the crust, you create folds, you thin the crust in the center, and then the asthenosphere needs to upwell to compensate isostatically the missing mass at the top. Yeah. So what this creates is like this upwelling creates melt because it's a decompression. You are bringing material up to shallower levels, so you melt a lot. And you would expect to have the volcano in the rift valleys, most volcanoes in the rift valleys, because this is where the melt would go vertically. However, this is not the case, and I have a couple of pictures. So this is again Ethiopia, and actually a lot of volcanoes are in the Rift Valley, but they are the very young ones. Because if you look at the very old ones, they are actually on at the side of the rift. They are way beyond the fault of the rift. So on the Somalian plate here, so you can see the pink are volcanoes. You can see here, and you can see here, and some of them are as far as here. These are the old volcanoes, 10 million years old. Why are they there if the melt is all in the upwelling is all below the rift? Why are they there? And this is another case, much more magma poor. It's Lake Baikal. Lake Baikal is in this location in Russia. And it is the deepest lake on Earth. It is 3 kilometers deep, the lake, and then below the lake there is a 10 kilometers deep basin with sediments. And this was also like a rifting event, for millions of years, that in this location, there was a suture between two previous plates that had collided and joined. And so these locations are often locations where you create rifts, continental rifts in the future, because it's anyway you have this weakness. So weaknesses are important. You have a weakness, and then you start to rift. If you extend, and this is Lake Baikal, and you can see that there are other rifts all around. These tiny rifts here and here and here. And there is no evidence whatsoever of any magma within the rift here. There is only one of these somewhere, I don't know if it is this one or this one, where you have some very, very early volcanism at the bottom of the rift, but then after a while all the volcanism was outside, and even outside by a lot, like here and here, quite far away from the rift. On the contrary, if you look in Iceland, magmatism is really, the vast majority is in the rift. So why do you have these differences, and why do you have volcanoes, so much of rift? I will skip this. Okay, so this would be like a model of stress if you create the rift. If you create the rift, so in the same way that the caldera was done, just with boundary element, in this case it's going to be boundary element. So basically you create the rift, you excavate the rift valley, and then you apply, to simulate this, you apply a decompression, that is the mass that is excavated and put away. Actually, it's completely different than in the caldera case. In the caldera case, you have actually going down and moved like this. In this case, you actually have a stretching that necks the crust, so it's actually very different, and you are going to have also different release stress. However, if you simulate it in this way, you will have that all the stress is bent like this. Instead of being like this, they become like this. So sigma 1 rotates, and you will have the same pattern that we saw in the caldera. And if you add some extension, because in continental rifts you have extensional stresses, then this is going to be your pattern. And if you look at the pattern, so where you see there are gray segments, this is sigma 3. And there are black segments or black circles, this is sigma 1. Where it is a circle, it means that actually sigma 1 is in this way, so against the page. Where it is a segment, this is the direction. So actually one can see from this figure already, before the simulation of the dike propagation, from this figure one can already see that actually the favored arrangement for magma is horizontal if you model the stress field in this way, because the decompression due to this mass removal is very big. Because if you create a valley that is 1 kilometer deep or even 500 meters deep, and you calculate the stress of this 1 kilometer is 25 megapascal, it's a lot of stress. It's actually much bigger than normal amounts of extensional stress that are more in the range of 5 megapascal, because if you raise it too much, then you are faulting. So you cannot raise so much extensional stress laterally, but you can excavate as much as you want, and you can build up very, very intense stresses. This is what creates this stress pattern that is creates horizontal storage. And then if you actually if you take the analytical formulas for the vertical stress and for the horizontal stress, and you calculate the here at the very center analytically, here at the very center, the relation between the vertical and the horizontal stress to check which one is bigger. Then you find that there are two locations, one somewhere here, it depends on the parameters, and one that can be very deep or even extremely deep, mathematically deep, I mean, not physically deep, even, you know, in the core. Then of course it's a different regime, you know, a different, they are the solution of, basically, if you ask your equation to check when the horizontal stress is going to be smaller or bigger than the vertical stress, to check where is the favored region where you have horizontal layers, then you get a depth that is between 2 points, and these 2 points are like these functions where everything is okay. What are these equations? This is the extensional stress, okay, and this is rho GD. This is the depth of the graben. So basically, the competition is between what extends in this way and what decompresses in this direction. And this competition is this parameter k. And if you put it in the equation, you get these two solutions. They are like, I call them Z sub 1 and Z sub 2, and everything will be scaled on with the rift width. So the rift width is also important because it will scale everything of these two Z parameters. So anyway, basically it comes out that if your rift is very wide and very shallow, then if you consider that the dikes are fed somewhere around this depth, then what you will get is that all the dikes trajectories will be kind of separated. So you will form a lot of eruptive centers everywhere in the rift, and all of them within the rift. If you have a very wide and shallow rift, this is like in Iceland, you have 300 kilometers wide rift and very shallow, you don't go very deep in the rift. And actually all volcanoes are there, and you remember the map of the Iceland with the fissures? You have several grabens and several fissures all within the rift system. However, if you have a deep and more narrow rift, then this stress area will be really strong and actually force any dike that are stored here, at least if the cross-mantle boundary is around this depth, all of them will be forced to be horizontal. And when they can escape and go out of the rift and create a volcano outside the rift. So it may be because of the distribution of stresses, distribution of loads at the surface that change with time, it will command where actually the volcanoes will be formed. In this case, outside the rift.
Does this explain our previous argument, the volcanoes on the footwall and
yeah,
king wall?
Exactly, similar, it's similar. Yes, exactly. Same argument. This is a tomography for Lake Baikal, where you can see that, so basically they had a range of stations all aligned, cross-cutting the lake. The lake is here, and here is this very deep basin with sediments just below the lake. And this is an entire tomography that reaches down to the mole. So first of all, they found several things that are quite interesting. The first thing that they found is that the mole is actually flat. There is no such a thing as a big upwelling there. Or actually, a stenosphere may be upwelling, but actually the mole is flat. And what they found, however, is above the mole, a region here with increased seismic velocities, like a more reasonable amount for the lower crust. For VP is 7.2 or something, but here in this region the values were higher, just below the graben, just below the rift. And basically they interpreted it also because they saw some reflections. So they rejected these two models with an expected more uplift, and with these faults that are a ramp, flat ramp, that is one possible model of rifting for this region. But they interpreted that here actually you have all the intrusives, and this is what actually increases your seismic velocity. Also they could see a lot of reflections. And so basically this is what the model predicts to be here. And then actually this justifies why they actually go so far away. If they start flat, then they go so far away due to all this stress. And I think the same authors have something on the main Ethiopian rift, where they also saw, maybe not entirely flat more, but almost, and also some of the volcanoes are outside. So skip. This is a map of stress. Okay, here like the parameters are, you can imagine this scaled up and down, but anyway, actually I wanted a figure that is similar, but where this point is a bit higher up. Because if you look at this figure, you can see that actually where it's red, the magma needs to be flat, and when it's white, the magma needs to be vertical. Okay, because it's the stresses flip. So basically, if you have these graben regions and extension, below this Z1 point, you will have the flat dikes. And actually in the upper dikes, in the Mandararo segment of the rifting episode that we saw earlier today, the magma chamber that fed all the dike this way, you remember it was flat. It was flat because actually that was the best model with a more flat magma chamber. This was also the same for Iceland, but also for the Afar region. And then from above, you have vertical dikes. So this flip also explains why you have this, because you have, why is favored to have a horizontal thing, and then from there you favor a vertical thing. This is predicted somehow by this model because you have actually a sudden transition between the points, between a region where you want to have them flat and a region where you want to have them vertical. So basically, an evolution model could be no evolution model. Why? I'll show you it. Must be somewhere else. I took it out by mistake. I looked into last year. But in which one? Is it here or not? I don't know. Maybe it's back there. Need I look at something else? Well, I'll show you tomorrow. I'll show you tomorrow the evolution model. It's better. So let's go back. Do you have questions about everything today? So let's make like a short summary. Definitely there are dikes. We have seen many of them. We have seen them mostly close to the surface, and the reason is because we have, with crustal deformation, a higher resolution on the very first 10 kilometers, let's say. It's very hard with crustal deformation to see something that is deeper. It needs to be really large for crustal deformation to see something deeper than that. However, we also see seismicity. We will go a little bit more. We will see how the seismicity of these dikes look like. It's important because basically all magma from the mantle to the surface is transported in this way. You do have these mashes magma chamber where you can have also porous flow, but generally they are fed by dikes, and also they feed dikes. Once you want to have an eruption from a marsh, a dike needs to be born, and it creates an eruption. And then once the eruption is created, if the magma is very explosive because it is viscous or there is a lot of gas, then what happens is that everything starts anyway with a fissure most often, but then you have an erosion of this fissure by the flow of the dike, by the flow of the magma. So basically the magma will, if it is explosive especially, it will erode the conduit, erode, until you create actually some wider space, and then you create a vent from the product, and then in the end you end up with a cone. But this doesn't mean that originally there wasn't a fissure. Most eruptions start like this. Okay, then there are other volcanoes where the magma is so viscous. Maybe it starts in this way anyway, like with a fissure, but then you have the magma becoming so viscous that in the end the most favorite shape for the magma is actually like a big worm, you know, to extrude, and then you will have this domes, you know. But this is because it's like a thermally stable situation after that you have had maybe in the long past a first fissure. I think most eruptions start anyway with something that looks like a crack. Then you can build a volcano, and then you can build, if your viscosity is really large, you can build these structures. So then you have other processes that contribute to a shape. Okay, then I presented today models of dikes where you only look at the trajectory, you don't look at anything else. I will show you tomorrow models where you only look at the flow and therefore at the velocity. And then I will show you that there are models now, very recent, where people try to combine the two, trajectory and flow. Because if you have trajectory and flow, then you are able to know where the eruption is going to be and also when the eruption is going to be. Because separately you cannot have this. You can have either a time but on the wrong trajectory, or a trajectory but you don't know when. You know only spatially more or less the directions. So we will look at this, and we will look also at the seismicity, and we will look at how the seismicity really looks like, and even try to find a way. Okay, there is an episode somewhere where I don't have much monitoring, because actually these regions are many. One is the big ocean. Okay, see seismicity there. I can't even have crustal deformation because we are in the ocean, or we are very remote somewhere. How can I understand if I have a magmatic episode or if it is something tectonic? Is there a volcano there that is becoming active? Do I have an eruption? Can there be an explosion? And what can I use to actually distinguish between tectonic and magmatic?
What plane solution may explain?
This will be a big component of it, fault plane solutions.
Whether it is expanding, if it is volcanic, tends to be explosive, therefore the P component of the seismic will be larger, because it's going to be like explosive radially outward. But for tectonic, tends to be shear, so P will be smaller and the shear wave this way will be larger.
This is the start of it, but it is actually, I will show you, it's definitely the background idea, but I will show you that there are a lot of details and, and variety, and you have to be careful about what is what. Yeah, no, it's like the background idea is this, but yeah, it's more complicated. Yes. More questions? Yeah, other things that I want to say? Well, anyway, I think tomorrow we will kind of finish finish. I mean, mention a lot of these dikes from a different perspective, more signals and monitor, both modeling and signals. Modeling will be more with this flow component to it, and the signals will be a lot of seismicity and focal mechanisms too. And also we'll show you also some analog experiments too. Yeah. And then we will see each other in 2 weeks after that. Yeah.
So is there any explanation for intraplate volcanoes? When we look at the map of volcanoes, most of them are on the interplate boundary, but there are some in the middle of mountains plates.
Yeah. So this explanation, I think it's a very, very important question that is not well understood. There are actually two big components to this question. And I think what the problem is that disciplines, you know, in geophysics, geology, geochemistry, they are still very separated. Like there is not much interaction between like geochemistry and geophysics, and this is probably a question that you need all the disciplines to address it, because to explain why a volcano is in a given location, I think you need 2 things. You need to explain why you have melt, where is the decompression, because most melt is due to decompression. Where is the compression occurring and why? Do you really have a plume? Because all the time when people don't know why a volcano is there, they say there is a plume. But not everything is a plume. You need some specific characteristics to actually justify a plume. Not everything is a plume. So then you need to explain why there is melt. Where is the decompression? You can use the composition of the magma to understand the melt process. You can use, you know, a lot of techniques that are geochemical techniques. Okay, and then this is one thing. And the second thing that you need is the trajectory thing, because actually trajectories we saw, they can be completely offset. So if people go and look for the melt source right below, it's not even necessary that it is there. It can be very offset. It can be somewhere else. It can be 300 kilometers somewhere else. So if you do a tomography, you don't like there and you don't see it, it's very deep. Okay, it might be very deep, but it can be also somewhere else. So you need experiments that look at tomography in a very wide region. You need maybe magnetotellurics, because magnetotellurics is a technique that gives you electrical resistivity, and it gives you therefore a picture of a lot of fluid pathways. And in magnetotelluric, there is a demonstration that these fluid pathways are not vertical. You can see a lot of these maps. They show everything goes in all directions. So I have so I worked also on this problem that you mentioned, why are the volcanoes intraplate and why are there, and I can show, so some of it is also, it was included in today's class, but I have another one that is actually, I think it's very instructive, so I can show you tomorrow at the beginning, which is about Mount Etna. Also, why is Mount Etna there where it is? There is no plate boundary. So actually there is a kind of a plate boundary, but it is in a mysterious location anyway, because also there were volcanism before the plate boundary was there, because it's a subduction. Well, I will show you tomorrow, it's complicated, I need the maps. Yeah, okay. So tomorrow we have at 9 o'clock, and then again in the afternoon. You have different other classes in the middle, right? No?
Like climate.
All the time. The climate.
The room is busy.
And where, of course, we are free.
We are
Yeah. Because we are attending this.
But it needs to be here because we need to record,
Yeah,
right?
I see.
In theory. Yes, okay. I will stop.